Okay, there we go. We're started. Okay, so I'm going to talk about visual data. Oh, this is really weird. I burned my fingers on my lawnmower last night, and like everything I touch feels weird now. Okay, I did remember. Thank you. Okay, so yes, I would suggest going and grabbing and installing Fiji. I do have the link up on the programs to install place. So I go do that. Okay, so let's launch into image and video data and how we go about collecting that and things about that and what's good about that. So first off, why do we even bother to use image and video data? Because in some ways it's kind of a hassle. It's why don't we just take 100 grad students and like stick them onto the things that we want and have them just like keep there with their little logbook or their little actually this is what we used to do all the time. And then get them with their little computer. I'm saying a lot, so forgive me. And you just have them like type in the data because hey, it's already in Excel if we make them do that, right? Well, there's a couple things that make this kind of recording of data a lot more efficient, a lot more desirable than actually sticking grad students on because sometimes a camera is better than a graduate student. And one of the big reasons is number one, it's more attentive than a graduate student. They don't blink. They don't need coffee, they don't fall asleep, they don't have to like go off to pee or something like that. And also we can follow subjects that are either faster or slower than what a human can follow easily. So this is another way that's really kind of nice to use this instead of something else. We can collect more data with fewer humans too. I mean, you have to sometimes pay humans or give them stipends or other things like that. And so cameras usually don't demand that. They haven't unionized yet. So we don't have to give cameras anything like that, which is kind of nice. Another really big thing is transparency. And this kind of comes back to like one of the general ethoses that I've talked about in science about being able to be open and transparent with your data. You can provide people with a series of images or a video that demonstrates, okay, this is where I got my data. Here, you can look at yourself and kind of come to the same conclusions or maybe different conclusions. If you just stuck a graduate student on it, and then they wrote down like the data or something like that, you can send them your graduate student, but it's not going to help them that much other than the data. They can tell you, yeah, that's what I saw, but that's how graduate students sound to me. Just joking. But that's not really going to like get the point across. The same way that if, okay, here, this is the behavior I observed. These are the cell flows that I observed. And you can actually send them the images or the video that document that. So that is another really nice thing about using this. You can also do more analyses in the future on this same data. So imagine at some point we're like, hey, but we got the speed that something is going through here, but what about like the vectors? What about the direction that they're going? There might be cool data in that. You didn't collect it the first time with a graduate student, you're like, well, I gotta do the whole experiment again. If you did it with a camera, okay, we have those videos, we can go back and do this next analysis on that same data. And also, this is another thing, just having a graduate student in the room can be disturbing to some things. Sometimes professors and sometimes organisms as well. So it can be less disruptive to the organisms having a little camera there monitoring rather than a person and you're like, how you gonna do next? Something like that. So, and that's just a few things. That's just a few reasons why we might want to use image data other than actually putting a person on this and watching something. However, that all leads to some big challenge. And that challenge is, how do we convert all of those images or video or anything else into quantifiable data? How do we get this into an analysis then that we can actually do something with? And so that's really what we're going to talk about here. Now, to begin this now, I am going to go through some image basics and some video basics. And honestly, a lot of this might be really, like you might know most of this already. So forgive me for boring you for the next 45 minutes or whatever it'll be. Just hang in there. We'll get into things that are more interesting. But I'm going to start with very basic stuff and then kind of march up from there. So bear with me. So let's talk about different image types that we can have. And the first one, which I'm going to talk about right now, but you need to be aware of so that you don't accidentally use them. but we don't really use for this kind of analysis, is vector images. Now, vector images are ones that, instead of creating an image the way we typically do, which I'm going to talk about next, we're creating an image out of a series of mathematical defined polygons and lines and other things like this. And so, if I have an image, I'll draw it over here. I have my image, or other some sort of thing, with a circle in it, and the circle is black. All I have is contained within some container a definition for the entire size of the image, and then a definition for the circle, and then, like, is the circle filled or not, and then what color is the circle filled with, and that's really it. And then it kind of moves up in complexity from there. If we have a line here, then we have a definition for, okay, we have a definition for that line. It goes from some point on this image to another point on this image. It has some thickness, it has some direction, it has some color, and we define these. Now, these kinds of images are useful for a couple of reasons. Number one, generally, they take up a lot less data, a lot less memory than other kinds of images that we're going to talk about in a moment. However, that being said, and also, there's no resolution limitations. If I blow up this area right here really big, it is going to look like that. If I take this right here and then blow this up really big, it will look like that. And that's kind of nice. As much as I zoom into this, we will never get to a point where we're losing resolution. However, this is not good for photographs because photographs are more infinitely complex than what these generally tend to be for simpler kinds of images, for line graphs and stuff that a computer produces, not something that is captured from the environment. So we generally don't use these for data collection. But you need to be aware of them so that, okay, you don't try to accidentally use them for data collection. The alternative to this, but more common, what you're probably more familiar with, is raster images. Raster images are an array of areas, generally squares, although sometimes hexagons as well, and sometimes a few other things. And each one of these squares then is called a pixel. And then each one of these pixels is assigned intensity. If it's a black and white or a grayscale, it's assigned intensity. Otherwise, if it's colored, we have a different sort of values assigned to each color space or each color in there, and we can define the color that way. If we were to zoom into a raster, then instead of looking at this like this, if we zoomed into this, we would have something that looked like this, because we have the individual pixels, and then if we zoomed into this, you would have, or this we have black, and this is white. So as you zoom in, you lose resolution, you get pixelation. Talk more about that in a few moments. And so there's several different kinds of color space that can be assigned to these. There's different ways of defining the color that we have inside these images. The most common is that we have RGB color space, where red, you have a value that's assigned to the red color, you have a value generally 0 to 255 that's assigned to green, and a value that's assigned to blue, and by mixing all of these, you get the color that you desire. Now, one point about RGB color space is that this color is additive, meaning that if you combine all the colors, you have red fully on, so a value of 255 for red, value of 255 for green, value of 255 for blue. If you have all of them added together, you will get white. It's essentially by adding all the different lights together. So imagine you're in a dark room and you have a green flashlight and a blue flashlight and a red flashlight, and you shine them on the wall. If you shine them all together on the wall, you will get white light. So additive color is kind of like light on the wall, like from flashlights. Another commonly used one is CMYK color space, which stands for cyan, magenta, yellow, and black. And this is a subtractive color space. Essentially, every time that you add a color, it is not returning all the other colors. So this is more like mixing paints. If I mix cyan, magenta, and yellow together, we are going to get actually like a muddy brown. You add all of them together, you don't get white, you get black instead. So this is a subtractive color space. Okay, so to kind of show you give you a little bit more of an example of this, imagine we have like this little smiley face here, we blow it up, and again, as you see we have pixelation. You can see the individual squares in the array that have then a different color assigned to each one of them. And in each of these, if this was red, green, RGB color space, we'd have then an intensity assigned to red, one assigned to green, one assigned to blue, and each of those then combine to make up the different color. So for instance here, we have low red, low green, but even lower blue, so you get kind of this brownish color. And then here we have very high red and high green, but zero blue added, you get yellow. And that is how a raster graph is built. Another really important component of an image then is not only this, but also its bit depth. This is going to be really important as we are looking at different kinds of images and what we can do with them. Now, the bit depth is how many bits are assigned to each pixel to encode its color or its intensity. So just kind of a brief refresher, a bit is a basic individual unit of digital communication. It can either be a 0 or a 1. So with every bit that gives us an on or an off state, we can have two different states that's in. So the most basic kind of bit depth that we can have would then be a 1-bit image, which means then only 1 bit is assigned to the color of every individual pixel, which means that it can either be on or off. In this case, it can either be white or black. One or the other. There's no grays, there's no intermediates, it is just one or the other. Slightly up from that is, but it's still common, and something actually you'll end up using in this class a little bit, is an 8-bit image. This means that we have 8 bits for every single pixel. Now, if you imagine this, that means then that you have 256 intensity levels. The reason for that is instead of just 8, imagine we have 8 positions, 1, 2, 3, 4, 5, 6, 7, 8. Each of these can be a 1 or a 0. So then each of these can be 0, 1, which means then as you go through, there's 2 combinations we can have here by 2, by 2, by 2, by 2. So the number of different intensities or levels that you can have is 2 then to the bit depth, 8, which then in this case is 256. Which is generally, we assign these then from 0 to 255. So if you open up something like Photoshop or something and are looking at the RGB color space and trying to assign a color to something, you usually have a slider that you can take, and you can slide it from 0 on a color to 255. And you may have wondered at some point, why in the world did they pick out 255? Why not like 100% or 1,000 or some round nice number? Well, 255 is round if we're talking binary. And so each one of those colors well, we'll get to that. Then leads to what's more common, 24-bit images, in which you have 8 bits for each of the 3 colors. So first you would have a block of 8 bits for green, a block of 8 bits for red, and a block of 8 bits for blue, or some, I don't remember what order that they're in. But then we have that for each of those. And then we can combine those 3 colors in any way. And so that's why you have those sliders on there that go from 0 to 255. That allows you to pick out any range of the colors that you can actually make with 24-bit image space or color space. And this leads to a grand total of 16.8 million different colors that you can make with that. Now, all that being said, these are not the only bit depths. These are just the most common ones I'm talking about right now. There's actually like 32-bit depth and 36-bit depth, and what you get there is not more colors, but then you get other things like alpha channels that lead to transparency of the pixels and other things like that. But really, for everything that we're going to be doing, one of these is probably going to be what you're working in, either 1-bit, 8-bit, or 24-bit color space. Let me give you an idea of what this would look like in reality. So, this is a 1-bit image. Now, it looks like there's grays in here. It looks like there's grays in here, but there really isn't. That's just the projector not projecting as well as it could. But what you have is you have a bunch of, you have a bunch of pixels in here. They're either on or off. It can be either completely on or completely off. So you get kind of a, you can do shading by having more or less of them actually done like this, but this isn't normally how you see it. With dithering on. If you have an 8-bit, now 8-bit can either be in color or in black and white. If it's in color, generally you have 3 bits for red, 3 bits for green, and then 2 bits for blue. But more common is that you have, especially today, is that you have 8-bit black and white, where you have then 256 levels that you can have of grayscale. And this is what you would see for a 8-bit image. It really just looks like a normal image grayscaled. And then here's a 24-bit image. So once again, 1-bit, 2-bit, or 8-bit, excuse me, and then 24-bit. Okay, any questions thus far? Okay. So after this we have video. Now, video essentially turns into, or is, a series of images that are encoded similarly to single images. However, all that being said, this becomes more complicated, especially as we start to consider video compression and other things like this. This becomes not exactly true. But for the purposes of what you need for image analysis, this is a good enough approximation. And from any given video, generally, if you have the right tools, you can extract all of the images that you want from that up to the frame rate. And this adds another dimension to your imagery, ideally, or specifically time. So not only do we have a single image which captures a certain small length of time, but now we have a series of them that actually gives you change over time, which is nice. And one other thing here that I don't have up here that you need to know about a video, one important part of that is you should know the frame rate. And the frame rate is the number of images that are shown by the video per second. So you essentially call this images per second. Now, a typical frame rate for things like if you were to go, like traditional movies are shown in 24 frames per second. Most other video is shot in very close to or exactly 30 frames per second, although a lot of video standards are actually 29.98, so very close, but and it makes a big difference over longer videos, but not over short videos. So approximately 30 frames per second. There's a really big push at this moment that 60 frames per second is becoming more and more common. 60 frames per second looks weird. Well, you get used to it, but the first time you see 60 frames per second, it looks amateurish. Because the funny thing is that, so what happens actually with your eye is that if you get 60 frames per second, motion is actually more natural, more like what it actually is in reality. And when you see that in a video, it looks not right. Generally what you have is something like you're used to seeing like movies in 24 frames per second. What actually happens there is you have some smoothing of movement. It looks less jerky, it looks more smooth, it's slightly dampened out. And that becomes, there's a little bit more motion blur in it, and it looks more movie-esque to you. And then if you look at 60 frames per second, this is why your life doesn't look like a movie, because you're actually viewing it at closer to 60 frames per second, which is about what what's called your flicker fusion rate in your eyes. The flicker fusion rate is the rate, essentially the frame rate that your eyes work at. It's slightly different. It's closer to 60 frames per second, so this more matches what you actually see, and then it just looks weird when you see it in a movie or a video, and it looks amateurish. And then obviously you can go, I mean, there is almost no top end to what, I mean, technology is the only top end, and I've seen things like thousands of frames per second if people want to get very slow motion up to, I think even, there's some cameras that do up to millions of frames per second. Anyways. And they cost a lot and I can't buy them. Okay, so, all that being said, imagery has its limitations. And I'm going to before we talk about image analysis, I'm going to talk about some of these limitations and some of these problems that crop up. And the main thing is that as you are designing an experiment, or as you are designing some data collection that's going to involve imagery, you need to have these things in mind so that you can minimize the impact of these different problems as you move along. Now, one thing that you need to remember is that anytime you have a picture, it's a two-dimensional representation of a three-dimensional or sometimes four-dimensional reality, including time. What you have in a single image is you have 2 dimensions and you're capturing something that is actually happening both in 3D space, but then also over time, and you do not have a time component there. And what this does is this induces distortions onto reality? Did I spell that right? Yeah. It looks weird to me. It does not look like reality to me. Which, now that I say that, is like more profound than I really meant that to be. Anyways, so if you're capturing your own images, you need to do whatever you can to try to minimize this as much as you can. However, that being said, there's only so much that you can do. And if you're getting images from other sources which you didn't capture, you need to be careful to watch out for these kind of distortions, or else you can process bad data. So, let's talk first about the limitations of the camera. Now, first off, the camera is only going to have some intrinsic resolution that it can capture. Now, the first thing is how these cameras are capturing things is essentially you have an array of sensors on what's called a CCD or CMOS chip, like a light-sensitive chip, and it only has so many sensors packed onto such a given size. And that is going to set the absolute upper end of the resolution that you can get. Now, one thing to keep in mind is that there is an upper, then that sets the lower limit of size that you can resolve in that image. There is a idea in signal theory called the Shannon-Nyquist sampling theorem, not theory, my bad. And essentially, generally this was first applied to radio signals and trying to sample radio signals. And what they said is that your sampling frequency needs to be at least twice the actual frequency of the signal to be able to fully reconstruct the signal. However, that being said, we can also apply, and it works the same for looking in spatial data as well. And if you're in spatial data, your resolution, your pixel resolution, or your pixel size has to be at least 1/2 of the smallest structure you are trying to resolve. So the small structure you can resolve is only twice the size of each pixel. If you get below that, you start having distortions in the actual structures that you are trying to resolve. So that's one idea to keep in mind as you're looking at this. Also, the sensor chip itself has some sort of spectral sensitivity. It's not the same as your eyes. The actual light that it is sensitive to is not going to be the same as what you can actually see. And this is something that you keep in mind. You look at the room and you think, oh, hey, I see certain amounts of things. A camera doesn't see those same things all the time. If you look at most CCD chips, this is the spectral sensitivity of those. They go from somewhere between 400 nanometers up to well over 1,000 nanometers, which is different, which is especially on the infrared side of things much farther than what you see. Only human eyes are only sensitive to about 400 to 700 nanometers. CCD chips have a lot more than this. Now that being said, to reproduce something that looks similar to what you're seeing, because most cameras and sellers of cameras want you to, like the pictures to look like what you're seeing, not some grotesque thing that you didn't see, like ghosts and things, because obviously they're in infrared. Talk about ghosts. Anyways, they actually have filters that will filter out most of this, so that it brings it down to more similar to what you actually see. Although that being said, a lot of modern CCDs actually pull it down to around 200 nanometers as well, so they're seeing into the ultraviolet that you don't see and into the infrared that you don't see. If you remove those filters, you make most of those chips sensitive to those again. A lot of camera manufacturers have seen this as a bug and not a feature to take care of. However, depending on what it's used for, that's also very useful at times, and that's sold as a feature instead, which all it means is that they've removed or they've never put on an infrared filter. So, but this is something to keep in mind, is that what range of light is my sensor actually capturing? And in some cases, this is going to be a problem. Now, I'm not going to talk more about that right now, but it's important as well. The other thing that we need to keep in mind is the aspect ratio. Because essentially, now, there's two different levels of aspect ratio. We could be thinking about aspect ratio of the entire picture, like how many pixels wide, how many pixels tall is it? However, that being said, we also have an aspect ratio of each of the pixels, the ratio of the height of the pixels to the width of the pixels in relationship to what there is in reality. Excuse me. So not always are cameras capturing a square pixel that is actually a square area of excuse me, a square area of physical space in reality. And we'll come back to that in a few minutes and talk about how that can change things. Some other kinds of distortion that we have, and this is not intrinsic to the camera, but the use of the camera. The first one is parallax. And this is a difference in the apparent position of an object based on the position of an observer. Now, this is kind of cool in a lot of ways. This is one of the first ways that we measure the distance to stars, is as we would like go on this side of the sun, the star would appear there, and then we go to this side of the sun as we rotate around, it appear kind of over here. And knowing the orbit of the Earth, we could get a good idea of how far a star was away, because it kind of changed where it was in the sky slightly, which is cool. But this can also cause problems if you were trying to capture an image and you're assuming that this two-dimensional image is accurately representative of a three-dimensional reality. If you're here, you have an object here, and you have a background here. This observer would see that object in front of the red blocks. If the observer is here and the object is here, it's going to look like it's in a different space. And so this is going to change the relative positions of things. Now, the solutions for this is to increase the distance between the camera and the subjects. And what this does now is, instead of having observer and things and having essentially viewing angles like this that are very strong angles, if we back up the camera ways, perhaps even use some zoom on that, and we're back here, the angles are now more gentle to everything, and you get less parallax. So that is one way that you can reduce the effect of parallax. The other thing is to decrease the variance in the distances of something away from the camera. So if we don't have, again going back to this, if this object is moved closer to this background, then the effect of parallax is going to be diminished as well. And so, it's kind of one general thing on there, trying to keep everything on the same level works well. That also works with the next thing that we're going to talk about, which is foreshortening. And this is the difference in apparent size due to the distance from the observer. I mean, this is kind of intuitive. You go a long ways away and you look smaller. And the solution to this is, again, trying to make all objects about the same distance from the camera, and that reduces that. We have things called chromatic aberrations as well. And this is a failure of a lens to focus all different colors on the exact same point of the sensor. This happens because light having different energies is going to refract differently through the same substance. So as it refracts through the lens, red refracts at a greater angle than, for instance, blue or green. In reality, it looks a little bit like this, or a less angle, I guess, for red because of the longer wavelength. Yeah. And so what you get is a convergence of different light at different depths. Now, there's ways of correcting this in the lens. Oftentimes, what they'll use is actually a different kind of lens after this that essentially bends it again. But this is what it looks like in reality. You take pictures. This is a very extreme example of chromatic aberration. We have like a red fringe on one side of an image, a blue fringe on another side of the image. You also sometimes get magenta and green, depending on what kinds of lenses that you get or something else like this. And this is going to hamper your ability to analyze these images. It induces blur that you don't really need. This can happen with electron microscopes as well, because you have electrons, and all electrons have the exact same energy, and they will resolve differently, having different energies as well. Now, the thing is that some chromatic aberration is inevitable at some resolution. Ideally, however, the amount of aberration that you have is less than the resolution of your sensor. And if that is the case, you don't have a problem. There's no detectable aberration. But at some point, it's very near impossible to fully resolve all colors at the exact same point. It's just very hard. The point is just to keep it smaller than the resolution of your sensor. Now, the solution to this, there actually isn't much that you can really do outside of a couple different things. Number one, use better lenses. Or number two, get closer to a subject. The more that you have to zoom in on a subject, the more chromatic aberration becomes apparent. And so the closer you are to the subject, the bigger it is in the field, the less chromatic aberration is going to affect subsequent analyses that you have to do. We also have a problem of motion blur oftentimes. This is a consequence of anytime you capture an image, you're not only capturing a point in time, you're actually capturing over a period of time. And if something is moving during that period of time, then we have the problem that you will get movement or a blur of that subject through the image. And a couple ways that you can solve this is a faster capture rate, or slow down your animal, maybe kill it or something like that, and it won't move as much. Or barring that, like for instance, in microscopes for a long time, there's this substance called protoslow that is essentially a thick, goopy stuff that a lot of things can still breathe in. They seem to do okay, but it's really thick and goopy, and it's so clear, and so it slows down things, and so you can take better images of them. It's kind of nice. And also we have noise that just happens, and often this is worse at low signal. So noise is kind of a constant, and it is a intrinsic, to a large degree, is an intrinsic property of the sensor that you have, depending on how the electronics are constructed on that. And at low signal or low light, the noise becomes more apparent, and if you get higher light or higher signal, then noise becomes less of an issue. And that looks like this. So you see all this graininess in this low light picture. This is a stack of books or a stack of papers, or I don't even know. And this is a table down here, but you see like there's all of this. There's a not even color or even texture through there. You have all this noise introduced. And again, low light pictures tend to have more of a problem with noise. And again, this is another thing that will inhibit your ability to analyze these pictures. And the ideal for that is to increase the light levels. Now that being said, remembering that CCDs are not just sensitive to visible light. Sometimes the solution to this is non-visible light, like infrared, to increase that, and you can get better images that way. Okay. So that's some of the things that you need to watch out if you're setting up an experiment that is using imagery, and some of the problems that often crop up that will hamper your ability to actually analyze an image. So let's talk about now some of the basic measurements that you can make inside an image. And some of these are going to be really intuitive at the moment, but we'll move on fairly quickly through this. The first one is distance. You can take a distance between objects that are in an image. Generally, we're taking the Euclidean distance, which is pretty easy. You just take the difference in x coordinates, the difference in y coordinates, and this is coordinates as pixels generally. Square both of those, add them, and take the square root, and you get the Euclidean distance. Sometimes as well, in some analyses, the city block distance is interesting as well. The city block distance, or the taxi cab distance, is, we have a grid. We're going from here to here. You can't go straight. And so the taxi cab distance is here, 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 here. Or here to here, which is the exact same distance. Or here, 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 which is the exact same distance. It's essentially adding this without the square, the absolute value of x1 minus x2, and the absolute value of x, or y1 minus y2, so essentially the entire x distance between them, or the entire y distance between them, add to the entire x distance between them. That's a city block distance. Generally not used in image analysis, but occasionally for some analyses become important, so it's good to be aware of that. Now, one thing that is important here is that we have an assumption of a 1-to-1 aspect ratio, that each pixel in reality is representing its height and its width are representing the same actual distance in reality. And if that is violated, then we have to do something to adjust for this. And one nice thing is we can actually calibrate this to true measurements in the environment. We can add something in there for calibration so that we can convert a pixel distance to an actual distance, like something in millimeters, something in centimeters. Again, this is fairly intuitive, but important. If you can get distances, then you can also get an area of something. And this is something that we'll come up to later. And one thing that images become very important for is finding area between or of complex objects. Can be a lot simpler in an image, actually trying to measure that out yourself. In fact, it could be work of a couple seconds rather than probably a lot of time otherwise. Another basic measure that we can make of an image is the distribution of intensities of the pixels that we have. What's the distribution of those values from 0 to 255 if we have an 8-bit grayscale? And that will look something like this. So you can have a scale of how many pixels are 0, have an intensity of 0, how many have 50, 100, all the way up to 255. And then you have a measurement of how many pixels are at or have each of these values. This histogram is relatively important. We'll come back and talk more about how we can use this later. But you may have seen this, a lot of cameras actually, you can get them to read out the histogram as well. And this is good in taking good photographs, because you don't want, when you're taking photographs, all of your pixels bunched up on either the dark side or the very bright side. That will generally mean that your image is overexposed or underexposed, depending on which side. So. But we can also use this in analyzing the image as well. From this distribution, we can also get a mean and a median of the distributions. We can get a standard deviation. How spread are the what this is. In fact, this is one of the very simple ways of measuring texture in an image, is to look at what is the deviation, the standard deviation of the histogram, and that gives you an idea of what are the different intensities. And then also a 95% confidence interval like we were talking about before. Are there any questions up to this point? Again, a lot of the stuff up to here is relatively basic. We'll get into Okay. So, as you start an analysis, generally one of the most important processes that you'll go through is what's called segmentation. Segmentation is dividing up the image into areas of the image that actually correlate to objects in the real world. Like imagine I have a picture of a coin, a pen. And this will be a very simple example. I have an image here. It has a penny in here. How do I decide what area of this image is the penny, is the subject that, or the subject in the real world, and how much of this is not penny? And that process of deciding what area of the image is penny or not penny, or whatever we're talking about, is segmentation. And there's several different ways of going about segmenting an image. Some of the common ones include thresholding, edge detection, region growing, and then morphological segmentation. Let's really briefly go through a threshold segmentation, and we will, because this is simple, I can go through this briefly. So, thresholding segmentation is one of the very simplest kinds of segmentation that you can possibly accomplish, and this is going to apply to the entire image as one. So it's known as a global segmentation approach. You can't really vary it across the image very easily. Now there are regional thresholding procedures, but it becomes easier to do different kinds of segmentation if you're going to do it regionally rather than globally. So thresholding is very good if you want to do it globally. And then what thresholding does is going to take your pixels and going to find a cutoff point in those and assign all of them above a certain intensity to white and all of them below a certain intensity to black. So if we come back here and look at, for instance, this histogram of intensity of pixels, it essentially takes at some level across here, it says, okay, let's make the level right here at 100. Everything that is below 100, we're going to just take all of these pixels and we'll just make them zeros, just blacks. Everything above 100, all of these are going to be 255 or complete white. So essentially we have taken a 8-bit image or something else like that and turned it into a 2-bit image, either white or black, and we're deciding that based on the intensity of the original. So, and this can also be done, you can threshold based on different colors, you can threshold based on the intensity, and this is one very nice strategy for dividing some parts of the pictures based from the others. We're doing this based on the relative intensity of those pixels. Okay, we're wrapping up there. We're going to continue on with segmentation tomorrow and probably pull out some specific examples of segmentation in Fiji. So if you want to follow along with that, we'll have that done by then. Okay, thank you very much. I will see you on Wednesday.